Okay, so next is Youngsung Chuang to tell us about DiffCSE, difference-based contrastive learning for sentence embeddings.
Okay. Hi, everyone. I'm Youngsung, a first-year PhD student from MIT. It's my pleasure to introduce our paper, DiffCSE, difference-based contrastive learning for sentence embeddings. This work is a joint work with MIT, Meta-AI, MIT-IBM, and UC Santa Barbara. In recent years, contrastive learning is changing the way of learning unsupervised representations. In computer vision, Sinclair makes two augmentations from the same image have similar representations in the embedding space. And this method enables us to learn unsupervised representation without any human labeling. In NLP, SimCSE is a framework similar to Sinclair, but it's for sentence embeddings. And it produces augmentations by changing the dropout mask inside the transformer layers. And it achieves state-of-the-art performance on many downstream NLP tasks. In SimCSE, an interesting finding is that the authors have tried many different augmentations and methods like random cropping, word deletion, word replacement. But surprisingly, none of them is better than doing nothing but changing the dropout mask inside the transformer layers. This result indicates that it's very difficult to produce useful augmentations for natural language because you can change the semantic meaning of the sentence just by changing one word in that sentence. So most of the augmentation methods are not very useful for contrastive learning sentence embeddings. Okay, now let's take a step back to think about why we need these augmentations. It's because we want to make the representations invariant to these kinds of augmentations. But the problem is that the quality of the augmentations is not very good. So an ideal representation should not be invariant to the augmentations. Otherwise, it will hurt the downstream performance. Does that mean these augmentations are not useful at all? Definitely not. Well, we can try to utilize these augmentations in a completely different way. We can make the representations be aware of, but not necessarily invariant to the augmentations. Let's look at some examples in computer vision to understand this idea. In computer vision, some of the augmentation methods like grayscale are very useful for contrastive learning. If we use grayscale to produce the positive pairs, we can achieve a much better performance compared to the baseline. In contrast, four-fold rotation is a very bad augmentation method. We can only achieve a worse result compared to the baseline. Now let's consider the opposite case. If we try to make the representation be sensitive to this augmentation, which means if we have different augmentation, the representation should be different as well. And in this case, if we make the representation be sensitive to grayscale, the performance becomes worse than the baseline. In contrast, if we make the representation be sensitive to four-fold rotation, the performance becomes much better than the baseline. So this result shows that all of the augmentation methods should be useful in some ways, but we need to choose the right way to utilize them. How can we have one model that has insensitive information and sensitive information at the same time? We can have a multitask framework as shown in this figure. On the left-hand side, we have a regular contrastive learning framework that encourages the representation be insensitive to grayscale. On the right-hand side, we use the model to predict the rotation angle of an input image, so we can make the representations be sensitive to four-fold rotation. And this framework is called equivariant contrastive learning. How can we apply this idea to learn sentence embeddings? Our framework is shown in this figure. On the left-hand side, we also have a regular contrastive learning framework that makes the representations insensitive to dropout mask augmentation. On the right-hand side, we have a generator and discriminator. The generator is a small and fixed BERT model that can replace some tokens in a sentence. And we use a discriminator to predict whether one token has been replaced or not. And someone may want to ask a question here. Isn't the model on the right-hand side called Electra? Yes, it's very similar to Electra, but a big difference is that the discriminator is conditioning on the sentence embedding produced by the sentence encoder. So the gradient of the discriminator will be propagated to the sentence encoder. So we can force the sentence encoder to compress the information of the input sentence as much as possible. And this will enable the discriminator to distinguish the tiny difference between the input sentence and the modified sentence. So basically, our model is doing a diff operation between two very similar sentences. That's the reason why we called our model DiffCSE. After training this whole framework, we remove the generator and discriminator and only use the sentence encoder to produce sentence embeddings for inference. In our experiment, we use the semantic textual similarity datasets to evaluate the performance of our sentence encoders. And we can see DiffCSE can outperform SyncCSE by 2 absolute points on the STS datasets. And it can also improve the performance on the downstream transfer task. Here we show a set of ablation studies to evaluate to prove that our model is the best design among different modeling choices. The first experiment is to remove the contrastive loss and only use the replace token detection loss to train our model. But the performance becomes much worse. So this result indicates that it's very important to have insensitive information and the sensitive information in the embedding space at the same time. The next idea is to use the next sentence as the input of the generator and discriminator. This will create a more difficult task for the discriminator. But the result is not better than DiffCSE. Another possible direction is to remove the generator and discriminator and only use a BERT model to perform conditional MLN training. But the result is still not better than using generator and discriminator. And in our experiment, we use MLN replacement to produce the augmentations. But we can also try other augmentation methods like insertion or deletion. But their result is not better than using NLM replacement. And here we also try to change the model size of the generator. And the result shows that the distilled BERT model is the sweet spot in among different modeling size. And if we use a stronger BERT model like BERT base, BERT large, or a weaker BERT model like BERT small, BERT tiny, the prediction task will become too difficult or too easy for the discriminator to learn useful information. Here we show the retrieval examples to see the difference between SyncCSE and DiffCSE model. Here the query sentence is, this is not a problem. And the top 1 nearest neighbor in SyncCSE's embedding space will be, this is a big problem. So this sentence has the opposite meaning. So it's a mistake made by SyncCSE because of the sentence structure bias. However, our DiffCSE model's top 1 choice will be, I don't see why this could be a problem. So this sentence have the right meaning but with a very different sentence structure. So this example shows that because DiffCSE can distinguish the tiny differences between similar sentences, so it will not be biased by the sentence structure. In contrast, SyncCSE are more easy to be biased by the sentence structure. We follow some of the prior studies to use alignment and uniformity to evaluate the quality of the embedding space. Alignment means the average distance between the positive pairs, and uniformity measures how well the representations are distributed in the vector space. Here we compute alignment and uniformity for BERT, SyncCSE, and DiffCSE. And we can, the scores, smaller number is better. And for SyncCSE, we can see that it can achieve a much better uniformity, but its alignment is still similar to BERT. However, our DiffCSE model have a much better alignment compared to BERT, but its uniformity is similar to BERT. So this result indicates that our model and the SyncCSE model are actually optimizing the representation space in two different directions. And our improvement maybe mainly comes from the better alignment. In conclusion, motivated by the fact that augmentations for natural language are not very useful for contrastive learning, we present DiffCSE, a new unsupervised sentence embedding framework that is aware of, but not necessarily invariant to MLN augmentations. DiffCSE can achieve state-of-the-art performance on SDS task and the downstream transfer task. And we also have a set of observation studies to demonstrate that DiffCSE is highly optimal among different modeling choices. Qualitative study and analysis also show that DiffCSE can produce a better embedding space compared to SyncCSE. Don't forget to check out paper and code. Thanks for listening.